Welcome to the ePathshala, the PG course for computer science student. We are discussing with respect to the course of embedded system, and in embedded system we are particularly concentrating on the ARM and Atom processor. So we already spoken about few classes about the ARM architecture and its instruction in our previous classes. In today's class we will actually try to concentrate on few rest more instructions that we have in ARM. We will also speak on how the privilege instruction gets executed and how we actually access and execute a co-processor instruction. We conclude ourselves by speaking a small concentration of discussion on the thumb instruction set, and we will see few examples of the embedded C program that incorporates the ARM microcontroller kind of scenario. Okay. So, to start with, among the classification of instructions, we already seen the data processing, control flow, data transfer. Today's class will actually concentrate on the last three: the software interrupt instruction and the program status register instruction, the co-processor instruction. So, software interrupt instruction. So, as the interrupt name comes into picture, interrupt handlers can run only in during the mode of where you have a supervised or a privileged mode. So, I have to give a call which has to run for under the concern of the privilege situation, a supervisor call. So, whenever I want to execute something which needs the support of the operating system, we will definitely go for this particular kind of instruction, which is basically a software interrupt instruction. So, some defined function which has to be executed under the kernel rights of the operating system. So, we can say that SWI, the software interrupt instruction, is a user defined privileged section of code that we want to run. So, as we always see, like whenever you go to a subroutine or something, you need to store your current status information. So, that is basically done by our SPSR. Okay. So, store your CPSR in your SPSR that belongs to the supervised mode of operation. Then it could be even with respect to our interrupt request kind of scenario, or it could be even with respect to our fast request scenario, when we tend to store the current program status register into the save program status register. So, generally when you move to this particular interrupt scenario, we always have a vector table which actually tells where are the different interrupt handlers available in the memory. So, that table is available at the location of 08, where we normally try to point to the program counter, from where we will actually start finding out what is the next thing that we need to execute. So, just like any other instruction, we need a offset value that actually points to this particular location, that it takes almost 24 bits, similar to our branching scenario. So, we can just imagine that supervisor call basically happens to execute privilege level of instruction. So, which can't be done directly under the user mode. So, we can just look on two examples over here, the SWI, which actually speaks about two different locations where I run some kind of a supervised subroutines which need the permissions of the operating system. Okay. So, coming to the next category of instruction, the instruction that are relevant to the register transfer with respect to the program status word. So, either I am trying to copy the content of program status word to the register, or the register's content to the program status word. So, if you just looked on the first one, MRS, where the CPSR of the current one is tried to be copied into the destination register, or maybe into the SPSR. So, if we just look on to this particular example, it is a 32-bit register, and even the CPSR and the R0, R1, R2 are the 32-bit register, where I am trying to copy the values of this CPSR or the SPSR into the registers R0 or R3. Vice versa of this previous scenario which we have spoken is our MSR, where I am trying to put a content into the status register. So, a content in the register field or some register that I am trying to point over here can dump its values on the status register. Either it could be our CPSR, either it could be our saved program status register. See, the RM value dumped into our CPSR or SPSR. So, it could be a register value that could be dumped into it, or it could be immediate 32-bit that is tried to be copied into this particular SPSR. So this instruction is a privileged instruction generally when I am trying to update the contents of the SPSR or CPSR. So generally normally an operating system will expect that this instruction runs under the privileged mode. So after the program status register, the third category of instruction that we are trying to speak over here is a coprocessor instruction. Coprocessor instruction, as we have already seen, like a processor, ARM processor can keep on extending itself, appending itself with some additional processor which are generally called as coprocessor, which helps in improving the instruction, the richness of the instruction set of the ARM, which can do additional processing apart from what ARM does. So at the maximum 16 coprocessor can be interfaced with the ARM structure. So each coprocessor will have its list of register which it may try to copy or transfer the content into the memory or the register of the CPU of the ARM processor at given period of time, or you may try to do some data processing kind of operation on this particular coprocessor register. So if you just look down with respect to the coprocessor, we can classify the instruction that the coprocessor can be put forth into three categories. One is the usual coprocessor data processing instruction, the coprocessor register transfer instruction, the coprocessor memory transfer instruction. As the name itself indicates over here, coprocessor data processing. So CDP. So just like we have data processing instruction, so it initiates the processor's data processing capability and those operations are expected to be executed over here. So when I say coprocessor register transfer, I am trying to transfer the content of the register maybe from the ARM to the coprocessor or from the coprocessor towards the ARM register. So if you look down, there are two over here, MRC, MCR. MRC move the ARM register from the coprocessor register. So MCR is basically copying like the coprocessor register from the ARM register. Then the same kind of copying, if you do it with respect to the memory, we normally call whom? We call the load and store kind of instructions. That is what is over here, LDC and STC. So load the coprocessor register from the memory or store the coprocessor register content into the memory. That is what is the LDC and STC kind of scenario. So speaking about this, we have almost listed all the categories of instruction that we have spoken in our past few classes: the data processing, the data transfer, the branch instruction, the swap instructions, the branch and the load store, that actually we are trying to speak the multiple content copy, multiple block copy, and the software instruction that we have just now spoken, interrupt instruction, the program status register instruction, and the instruction that we have lastly concluded is our coprocessor list. So all these have been listed over here. So few examples of our data processing: add, and, okay. Then these few examples of our branch instruction: B, BL, BX, okay. Then there is an instruction which basically says bit clear. It's a category of data processing itself. We're just listing out in a chronological order over here. Then comes a coprocessor instruction, compare instruction, compare negative, okay, exclusive OR, loading from the coprocessor, loading multiple contents, multiple register copying, loading with the register either by a byte or either by the half word or either by the total full word kind of scenario. Then MCR, MLA, multiple accumulate with respect to the multiplication and barrel shifter kind of scenario. Move instruction, MRC, MRS, all these instructions which we have until now spoken with respect to all the categories. The multiply instruction, the move negative. So normally when I want to copy complement of a content, so move negative, ORing, reverse subtract. So generally the tendency is when I say subtract R3, R1, R2, it's always R1 minus R2 which is stored in R3. So if I say reverse subtract, is generally R2 minus R1 kind of scenario that we are trying to store in your R1. So that is what has been shown over here. The destination, it's basically operand 2 minus the operand 1. The R1 basically stands as the operand 1 over here. Subtract, then store coprocessor register, store multiple, all these, okay. The store register for the memory, then the subtract of software interrupt, swap, test bit, test on equality, Okay, so all these are the categories of instruction which we have seen until now. After the instruction set that belongs to ARM, next that comes into picture is our thumb instruction. The thumb instruction, if you remember back, we said like ARM instruction are of 32-bit, the thumb instruction is of 16-bit. So it has to be more compactly encoded and it should be a denser kind of implementation. So with lesser number of bits I should be able to equally tell the same subset of operation that we were actually speaking with respect to the ARM. The same addition, multiplication, everything that should be possibly done by ARM should also be done by the thumb instruction. Maybe few operations we may let go because of the insufficiency of number of bits that is available with respect to the thumb, but it creates a compact encoding that we are trying to put on with respect to the thumb. So, it is a 16-bit encoding scenario over here. So, 16-bit instruction where we are trying to optimize the code density. So, lesser number of bits, equivalently vibrant amount of operation. So, lesser number of bits ultimately means what? You are using less amount of memory. So, that is what it actually shows, improved performance of memory. That is less amount of memory, more operations. Then ultimately what this thumb instruction tries to do, it does the same sequence of operation that we actually have even in the ARM. So, since it is 16-bit, all operations are not possible, only maybe few have to be let gone. So, it is a subset of the ARM instruction set. Okay. See, core with respect to our ARM core, as we already said, like it always has two states, ARM state, thumb state, and we can switch from the ARM state and thumb state at any point of time. So, how do you switch? As we said, we have instruction called as branch exchange or branch link exchange, which actually helps us to change or modify the thumb bit. So, whenever the thumb bit is 1, it basically says that I need to go to the thumb instruction set and execute the instruction that belongs to thumb category. When the thumb bit is 0, and even there is one more bit which is actually called as a Jazala bit. Even the Jazala bit is also 0, basically we are trying to execute the ARM core instruction. So, when I say Jazala is 1, we are actually trying to execute the Java bytecode. Since we are not speaking about the Java bytecode currently, we are only concentrating on the thumb kind of scenario. So, what are the additional thing that your thumb has to let go, because it is actually using less number of bits. One key thing that it is actually letting go is trying to append the conditions. If you look back to our ARM instruction set, all the instructions can be appended with a conditions. So, which can help the instruction to be decided whether it has to be executed or whether it has to omit the execution of that particular instruction, like subtract greater, equal, less than, all that kind of scenario. So, if I do not write that condition, it always means as like it is like execute always AL. So, our thumb instruction actually follows that first scenario, default thing, it is a AL kind of scenario, where I will say execute always, do not worry about the condition, or maybe you can't have the freedom or the richness of condition that could be provided over the, since we have less number of bits over here. So, thumb instruction are executed generally how? It is executed unconditionally. And one more major differences, or maybe you can say the key characteristics of a thumb is ARM has a 3 operand instruction. For example, if I say add, it is add R1, R2, R3. So, R2 plus R3 add, store it in R1. With respect to thumb, it is only a 2 operand instruction or 2 address format. 2 address format in the sense, when I say add, I will say always add R1, R2. So, one of the source register happens to be your destination register itself. So, R1, R2 in the sense store R1 the ultimate result, like add R1 and R2 then store it back into the R1 itself. So, it is a 2 address format. Okay. So, due to its 16-bit kind of thing, it is more compact, and the instruction that we have in thumb are generally less regular than that we use in your ARM over here. Okay. And because of its dense coding, I do not need much of the bit information that has to be stored over here. Coming to the registers. So, we said like we have a list of registers which are available in ARM. So, those registers are also available with respect to them, but we are not given the entire set, we are given the lower half. Okay, starting from R0 to R7 is a section of register which is generally being given to the thumb instruction set. So, when I say add R1, R3 and all, right. I can use any register which is normally coming within the range of R0 and R7. And apart from this general purpose registers, we will always have some special function registers like program counter, stack pointer, the link register. So, those instructions or those registers are generally fixed, R13, R14, R15, which works as a stack pointer, link register and a program counter. Speaking about the state, once I am ensuring that I want to work in the thumb state, so what should I do? First thing, put the thumb bit as 1. So, when you put the thumb bit as 1, you automatically execute instructions that are belonging to the thumb set. Putting the thumb bit as 1 and expecting to execute the ARM instruction will actually create some exceptions. The same thing is vice versa, like putting the thumb bit as 0 and trying to execute the thumb set of instruction will create an exception which has to be handled appropriately by the operating system. So, we do not want to do such kind of wrong way of execution. So, when I say thumb bit is 1, I am trying to execute the thumb instruction set. When thumb bit is 0, I am trying to execute the ARM instruction set. Okay. So, you have to always manage things like according to the thumb bit, what do you actually try to execute over here. So, when you start with, always the ARM at reset will try to execute the ARM instruction set. As we said, like whenever you want to go to the interrupt handler mode or you want to go to the privilege mode, it will always try to execute the ARM core instruction set. Okay. So, it is generally like with respect to the embedded C kind of scenario, we will normally try to pick up the thumb set rather than the ARM set, maybe because of the choice of amount of memory that is used by thumb, which is lesser compared to the ARM kind of implementation. Thumb instruction. So, speaking about the thumb instruction, it is a fairly clear indication that thumb instruction is quite very simpler in terms of like it does not have more operands. Because it does not have more operands, what I tend to lose one of the freedom of retaining my source operand content. I overwrite it with my destination value. So, since I do not have one operand into it, maybe I need more number of instruction to execute the same section of code that would be done by the ARM instruction. And one more key thing that we told just now, like no conditional execution, you do not have that post fixing the conditions to the thumb set. Okay. And one more thing that it has to let go is, like if you look down into the architecture of ARM, one of the operand comes via the barrel shifter. So, we can do many shifting operation when the operand comes via the barrel shifter. Here we do not have such kind of operand scenario, like it does not comes via the barrel shifter. So, if I need to do a shift operation, that could not be done along with your regular instruction. You have a separate instruction for doing a shift operation, whether it is your logical shift or whether it is your arithmetical shift. So, we have a separate instruction for shifting. Why we have a separate instruction for shifting? Since it does not have the freedom of taking one of the operand via the barrel shifter. And one more key difference that we had seen with respect to ARM and thumb is, like in the ARM, whenever we are executing the data processing instruction, it does not updates our status flag. So, whenever I want the instruction to update the status flag, I will always append a bit or a letter called as S there. So, S basically means, like when I say add S, it basically means when you execute this add instruction, whatever the outcome of the status flag happens should be updated into your CPSR. That will be done only when I put S. If I do not put S, it will basically understand that I do not need to update the status register. So, we update the status register only for compare instruction. Okay, there are some selective instruction when you try to update your status instruction. It does not get updated for the data processing instruction. Whereas in thumb, all the data processing instruction assumes like it has a default S character along with it. So, whenever you execute a data processing instruction, it will automatically update the status flag. So, you do not need to specify the S separately or explicitly. And speaking about the syntax, we are not going into the thumb instruction much of detail as we are done with respect to ARM, just glancing through few section of thumb instruction. So, syntax could follow with respect to like the different operation, or basically mean the different operation that we try to do in ARM, similar to in thumb. It could be add, logical shifting, anything. that we try to do either data processing or data transferring kind of scenario. So with respect to data processing, I can think about ANDing, ORing, exclusive ORings, subtracting, or adding, multiplication, all these things. So different syntax based on the addressing mode. It could be, because as I said, like it's a 2 operand kind of scenario. So operand 1 and operand 2, or maybe I can have one of the operand as the immediate value. Okay. So it could be other, like another way, the one of the operand could be a immediate value which could be shifted in 3 bits, or the immediate value of like 32 bit, or the immediate value of 8 bit kind of scenario. So these are few examples of the data processing instruction that we were actually speaking just now: addition, subtraction, negation, complementing. Then as I said, like you don't have the freedom of using the barrel shifter, so I need a separate instruction to do all the shifting process, either shifting, logical shifting or arithmetic shifting, either the left side or the right side, or the rotate right kind of scenario, where we will actually even take the carry along with and try to rotate. Okay. So just glancing through few on the data transfer kind of instruction, which is basically the load store kind of scenario. The similar kind of implementation, loading and storing, which could be of byte, which could be for half word, and one more thing that comes into picture is loading the signed representation. So either it could be half word or byte that I am trying to. So if you just look down, we are not speaking about the store over here. So generally loading needs that extension with respect to the extending the bit in your register that comes from the memory, where the signed bit has to be extended. So load store for data transfer. Okay. So what are the different things, or maybe the limitation that we could put forth for the thumb instruction? As we said, like most instruction that could be generated by the compiler over here for the thumb set does not have condition, like condition execution is not used. Then the source and destination registers are identical, and only the lower section of registers are used, as I said, like R0 to R7. Then the constants are always limited. We can't have many constants that could be put over here, and the inline barrel shifter is not used. So these are few limitations of our thumb instruction. After speaking about the thumb instruction, we are trying to concentrate on something which is relevant to the embedded C part of the ARM processor. So where I can actually program a C microcontroller using the embedded C with respect to the ARM processor. So the example that we are taking over here, trying to consider over here, is the LPC2148, which is the ARM 7 series of processor, which is basically ARM 7 TDMI processor. So if you just look down over here, this is a pin diagram of our LPC2148 kind of scenario. So each, if you just try to analyze on this particular pin diagram, most of our pins over here, okay, except few which has only one task to be done, which could be either VCC or ground or reset or this extal for the oscillator purpose. Most of our pin has multiple functions. It could be working like a port, it could be working like a transmitter bit for a UART, it could be working like a ADC bit, it could be working like a digital bit. Okay, so maybe maximum 4 tasks. The LPC 2148 of our ARM has pins which has multiple functions. Okay, so what function does this particular pin has to do, that will be told by some specific set of register, which will actually indicate how the pin should be working, like what functionality that actually they have to perform. And one more thing that we can actually observe in this particular pin diagram of LPC2148 is, like if you just look down, everywhere we kind of mention like P1 dot, P0 dot, okay, P0 dot 17, P0 dot 16, P0 dot 15. So basically P0 and P1 are the ports over here. The LPC2148 has 2 ports, P0 and P1. Each port is of 32 bit, just like ARM is a 32 bit architecture that we are considering over here. So each port is of 32 bit, okay, which can be either treated as entire 32 bit, or which could be read or written taking the half word 16 bit at a time. Okay. Now how do I treat these ports? Basically comes in terms of the control register that I use to define the operations of our port. Before we actually look into the control registers of this particular 2148, a few glances on what we have with respect to our 2148 LPC 2 It has a on chip memory which is of 32K of SRAM and 512K of kilobytes of flash memory, which could be used for both for data as well as the instruction. So, which is capable of storing even the byte, half word or the word. Apart from that, as it says like TDMI, like each alphabet actually has an acronym with respect to what extension that it does in the ARM over there. So, it has a serial debugger, the JTAG debugger, it has a UART device, it has a in application or in system programming that is possible over here, IAP or in system programming. Our embedded C example that we have taken with respect to the ARM over here is with respect to the interfacing of a buzzer and a LED. So, we are trying to speak about the ports which are being used as a IO, input and output. So, the ports 32 bits of P0 or 32 bits of P1 can be accessed either as the entire chunk of 32 bit or can even be accessed as a individual pins. So, as we said, individual pins which are available on this chip can have multiple functionalities. So, an example which actually shows over here P0.8, the port P0, the 8th bit of the port P0 can work as an input and output pin for the GPIO, the general purpose input output pin. It can even work as a transmitter bit for the UART, it can even work as a bit for the PWM, it can even work as a bit for the analog digital line. Okay. So, what are the registers that are actually controlling these ports? So, which registers? We have IO pin, IO direction, IO clear, IO set and IO select. IO pin, whatever is my current content of these ports can be read via the IO pin, okay, or what is it currently reading or what is it currently writing. The values of the particular ports can be always seen on IO pin. IO there is basically with respect to telling whether the pin should work as an input line or whether it should work as a output line. So, input line or output line. So, if I am working it as an input line or output line, if I am intending to clear a particular pin or if I am intending to set a particular line, so that could be done using the IO clear and IO set. So, if I want to set P0.8, so I should go to that particular line, okay, then I use IO set and put P0.8 as 1. So, it will set that particular bit. If I want to clear P0.8, use IO clear, go to P0.8 and put a value 1 there, it understands that I need to clear this particular bit. IO select, we said we have 4 different functionalities, right. So, that could be selected by our IO select. So, IO select 0, IO select 1, IO select 2. So, each port is divided into 2 halves. So, IO select 0 and 1 is for the lower and upper word of the port 0, P0 0 to 15, P0 16 to 31. Whereas IO select 2 is for the upper half word of the port 1. Port 1 lower half word is not available for GPIO, so only the upper half word. So, whenever I put IO select with 0 0, it basically means I am trying to utilize it for GPIO. So, we are not speaking about the different other functionalities that we have for 0 1 or 1 0 or 1 1. So, using IO select I will be able to tell whether I am using it for GPIO or not. So, what should I do? I should use that IO select, put a value of zeros over there. Then whether it is working like an input line or output line, who does? It is been told by the direction. So, 2 ports, right. So, IO 0 direction, IO 1 direction. So, for port 0, IO 0. For port 1, telling the direction will be IO 1 direction. So, 1 says it is output line, if I put there, if I put a 0, it is a input line. And IO set and clear for setting and clearing purpose. So, all these definitions of setting, clearing, direction is all available in the file that has to be included for the embedded C, which is your LPC 2148 or generally it is named as 21xx dot header file. So, this is a small example for a previous set of control registers which you have taken. This is a small buzzer program. The buzzer has to be on and off for few intervals of time, okay, which is continuously onning and offing kind of scenario. So, we have a small delay program, a delay which actually runs it for like some timer which has to be elapsed for a period of time. So, this is a delay that we have over here. The main has first few things that has to be done, the setup kind of things, like pin select 0 basically tries to tell whether I am going to select the GPIO function for it or not. So, since I am only using as a GPIO, so pin select 0, pin select like IO select 1, IO select 2, IO select 0, all are been put with a value of zeros, 32 bit, right. So, hexadecimal, 8 digits of hexadecimal. And buzzer, when I am speaking about switching on or offing a buzzer, it is always trying to send a value to it. So, I want it to work as a output line. So, if I am assuming that the buzzer is connected to the lower byte of the higher word, so FF, we are sending FF there. Why? Because the port 1 is what is connected to the buzzer. So, for that buzzer I need to send a value. So, it should work like a output line. So, I will send 1 on the IO direction. So, that is what has been done. So, you have clearly indicated that you are using it as a GPIO, we are using it as a output line. Now, what do I need to do? I need to send 1 and zeros alternately. That is what we are trying to do over here. IO set and IO clear. Since it is with respect to port 1, so IO 1 set, IO 1 clear. So, we are setting using this particular instruction and we are clearing it using this particular instruction, which is done alternatively via a delay. So, this is a small example of the embedded C for buzzer. Similarly, we can even analyze this LED program. You can just go through this LED program, which has a series of array that can be run on a LED which is connected to the ARM architecture. So, I leave it to you all to just track these lines of code that is available for switching on the LED on and off. So, concluding today, we have finished off all the instruction categories of the ARM. We have glanced through few about the thumb instructions also, and we have seen how a embedded C program can work or can run with respect to the chip which you are considering over here is your LPC2148, which does a small programming over here with respect to the IO interfacing of the buzzer and the LED. So, with this we will try to stop over here and conclude our classes on ARM processor. We next will start with another advanced processor. Until then, bye, take care, thank you.